without dropping the last part of electrolysis, some serious students reached out to me. They said, what are the formula used in electrolysis in solving some questions? Most questions in electrolysis. So let me write down the formula and tell you how to use the formula in case you are answering jam questions. So you are expected to know the following formula. The first formula, we have Q is equals to IT. We don't know what Q stands for. I will write all this out. So where Q is equals to quantity of electricity in coulomb, or you leave it in farads. Remember, 1 Faraday is equals to 96,500 coulomb. That's the conversion. Where I is equals to current in ampere, current in ampere, capital H, that's unit. Where yt is equals to time in seconds. Take note of that. That's the first formula there. The second formula, in the Faraday's first law of electrolysis, we state that the mass of a substance deposited is proportional to the quantity of electricity passed, where Z is a constant known as a electrochemical equivalent. So where M is equals to mass of a substance deposited, mostly in gram, usually in gram. While Q still remain quantity of electricity still in coulomb. That is capital C. While Z is equal to, we call it electrochemical equivalent. Equivalent of a metal. And you know the unit, usually in gram per coulomb. Take note of that. This is another formula. This one can be written, you can write this as M is equals to ZIT. So vacuum is equals to IT. So you can say ZIT. Take note of that. Formula 3. The same Q is equals to, we call it NQF. This formula is very, very important. Let me show you how we normally derive this. So where N is equals to number of moles of a substance deposited at the electrode, while Q is equals to charge on a metal, the charge on a metal or on a substance, this charge. Where F is equals to Faraday, which is 96,000. You still remember 96,500 coulomb. That is what 1F is equivalent to. So for Faraday, this formula is very, very important. Very, very important. So let's see how we normally derive this formula. 1 mole of a substance deposited at the electrode is equals to, meaning it requires, okay, let me say it requires, we can say 2 Faraday. If it is a monovalent element, you say 1 Faraday. If it is divalent, we have done it, you say 2 Faraday. If it is trivalent, you say 3 Faraday. If it is like aluminium now, it will be 3 Faraday. Like magnesium, it will be 2 Faraday. Like silver plus 1, sodium, it will be 1 Faraday. So let me say Q Faraday. Q Faraday. Where Q is equals to the charge on a substance, on an element or metal, on an element, e.g. monovalent elements. For monovalent element, Q will be 1. For divalent element, Q will be 2. Trivalent element like aluminium, Q will be 3. That's the meaning of this Q. One Faraday, you still remember? 96500 coulomb. So 1 mole require this. So 1 mole of an element deposited or substance deposited require Q Faraday. Therefore, N mole, what will be the quantity? You know this one is the quantity Q. So therefore, N mole we don't know. So we say N times Q F. You know we are looking for the quantity. This one is quantity. So Q now is equal to NQF. This is how we manage to get this formula to be NQF. That's formula 3. Please take note of that. Another formula for quantity of electricity is NQF, where N means number of mole, where N is equals to number of mole. This one is charge on a metal or an element. This one is Faraday 96500 coulomb. That is formula 3. Formula 4. From Q is equal to NT, you can say from Q is equals to NQF, but Q is equals to IT. So you can say IT is equals to NQF. This is another formula. Very important. So this one is written as IT. You can still use this formula. Number 5. Recall. Okay, let me write the formula before telling you how to use it. Q is also equals to MQF all over A. MQF all over A. Since number of mole is equal to mass of a substance deposited all over the atomic mass or mass number. So all over atomic mass, meaning mass deposited. There's a mass of substance deposited, mass deposited all over atomic mass. So that's what is written as M all over A. So where A represents atomic mass. Take note of that. So substituted for N. Anyway, you see N here. N is equal to M all over A. Just put M all over A, term of mass. This is another fine formula. Making 5. 6. We have IT is equals to MQF all over A. Since Q is equals to IT, you know, This one is derived from Q is equals to MQF all over A. So anywhere you see Q, same thing as IT. So that's how we managed to get formula 6. Formula 6. Where M is equal to mass of the substance represents where this one is mass number of that element or atomic mass. So number 7. Another formula we need to know in terms of volume, if it happens to be gases like oxygen and coal. So how do we determine the volume? Anytime you have to find the volume under electrolysis, you say V is equals to Q times 22.4 dNq. In case you're having in dNq, please take note of that. Divided by QF. That's how to find the volume. Everything in dNq. The volume in dNq. Let me remove it and put it. So this answer will be dNq. But using it in CNQ, it will be E is equals to Q times 22400 over QF. Will now be in CNQ. This is the formula for finding the volume. How do we manage to get this formula? Let me tell you how we manage to derive the formula. 1 mole of a gas, evolves either at the electric occupies 22.4 dNq at STP. This is what we know. 1 mole of a gas occupies 22.4 dNq at STP. And in electrolysis, 1 mole of a gas or of a substance required Q Faraday. I've explained this. Where Q is equals to number of electron or number of charges, N charges, number of charges, or the number of electrons, or the number of electrons, or the charge an element carries. Remember, for oxygen, we have done it. E.g., oxygen, our Q will be, the charge of oxygen is 2 minus, then times this 2, so it will be 4. For chlorine gas, chlorine is minus 1, then you multiply by 2. We have done it. Go and check my video. So it will be 2, and so on and so forth. This is how to calculate Q for gases. So that's the meaning. So like oxygen now, 1 mole of oxygen gas will require 4 Faradays. 1 mole of chlorine gas will require 2 Faradays, and so on and so forth. So that is what we are. This equation. 1 mole of the gas is equal to this. This is what we have. And it means 1 mole of a gas, Q Faraday, requires 1 mole of oxygen occupies 24, and 1 mole is equivalent to QF. So 22.4 QF will occupy QF, which is required to liberate 22.4 dNq of a gas at STP, because we have said 1 mole is equivalent to this. So it means this and this are equal. DF, this is the quantity of electricity required to liberate 22.4 dNq of oxygen at STP. So therefore, let's look for Q. If you have Q, what will be the volume here? So we want to calculate. Let's say you are given quantity, what will be the volume? So it will be Q times 22.4, you can see, divided by QF. This is how we manage to get this volume. So that's the formula. So it's the Q times 22.4 divided by QF. Please take note of that. 8. You can easily make Q the subject of the formula. You know, we said V is equals to Q plus 22.4 all over QF. Cross multiply here. We have BQF is equal to Q times 22.4. I want to make Q the subject formula. Q now will now be volume QF divided by 22.4. So will now be in DN and DNQ. Take note of I've made Q the subject of the formula. So when you know this formula, then you make one subject, or you know this one only. It's okay. You stop at 7 and forget about this. You can only achieve by making Q the subject of the formula, and you see how to apply all these formula. Very, very important. Very, very important. Very, very important. Very, very important. So number 9. Number 9. We have M1 all over M2 is equals to Z1 over Z2. This is from Faraday's second law of electrolysis. That is what we go and check my feed there. Where Z, this one does not mean electrochemical, it means chemical equivalence, not chemical equivalence. It's not the same thing as electrical equivalent, chemical equivalent, which is equals to atomic mass all over charge. Take note of that. Go and check my video under Faraday's second law of electrolysis. You will see how do we obtain Z1 and the formula. The formula. There are two formula for finding under Faraday's second law of electrolysis. The first one is written in terms of mass and chemical equivalent. The second one is number of mole. N1 over N2 is equals to Q2 all over Q1. You see our video, you see there, where the number of moles of a substance deposited at the electrode is inversely proportional to the charge it carries. While this is mass of a substance deposited at the electrode is directly proportional to the chemical equivalent. These are the formula we have. Where N means number of mole, where Q means charge. If you still remember, if you have sodium now, this charge is +1, so Q will be +1. That is 1. If you have aluminium now, the charge is 3, so Q will be 3, and so on and so forth. These are the formula we use under electrolysis. See example 1 on how to use the formula we have derived. We said how many Faraday is required to deposit 9 grams of aluminium. How many Faraday is required to deposit 9 grams of aluminium? You know, from the look of the aluminium now is 20, the mass number is 27. So this is what you are going to do. Q is equals to, you still remember, I say NQF. This is the number of mole. This is the charge. This is a Faraday. But this one has to do with mass, not mole. In that case, the formula you are going to use will be MQF all over A, where N is equals to N mass all over atomic mass. Take note of that. The mass of a substance represent all over its mass number will give you the number of moles here. So this is what you have to do. That's all. So you have to find Q. How many Faraday? That is, they want the quantity of electricity in Farad. That's the meaning. So you say Q is equals to, what is M? 27. What is Q? Q is the charge, like aluminum is 3 plus. So Q is equal to 3. So you say 3. Faraday, let me leave this out. How many Faraday? Let me leave you in Farad all over atomic mass. Mass of aluminum is 9. Rather, sorry. This is 9. So all over atomic mass, that's 27. So 9 here, 1, 9 here, 23 is the 1 Faraday. So is equivalent to 1 Faraday. So if you like, convert this to Coulomb. It will be 1 time, that is 96500 Coulomb. That's the number of Farad. That is what we are, 6,500 Coulomb. Straightforward. Straightforward. That is example 1. So let's see example 2. How many grams of aluminium is deposited by passing 3 Faraday of electric, no, let me say 2 Faraday in this case, of electricity. So aluminium still given as 27. That's the mass number. So if you use the formula again, Q is equals to Q is equals to NQF. This is what we have. There's in terms of mass. It's a mass. So the M all over A is the formula. So by passing Q is equals to 2F. So this is 2F is equals to M, I don't know. Q is 3 for aluminium charge all over F, everything all over 27. You can see F cancel F, make M. M9 is equals to 2 times 27. Example 3. Example 3. Calculate the mass of sodium deposited by the passage of 9650 Coulomb of electricity. Take sodium to be 23. That's another thing you need to know. So you apply the formula, the same mass. So in terms of mass, this is what we are going to do. It will be Q is equal to NQF, and in terms of mass, it will be MQF all over A. That's the formula. So we have to find the mass. Q now is not going to be 9650. So I'll say 9650 Coulomb is equal to M. We don't know M. What is Q? Sodium is 1. The density of sodium is 1. Times, what is F? Faraday. 1 Faraday. Take note of that. Take 1 Faraday is equal to 96500 Coulomb. So 96500 divided by 8, 23. That is exactly what you're going to do. So in this case, make M the subject of the formula to be 9650 times 23 divided by 96500. So you are going to have your answer here to be 2.3. So you are going to have 2.3 grams of sodium. So calculate the number of mole of uh, aluminium deposited at the electrode by passing 1.5 Faraday of electricity. So take aluminium 7, 1 Faraday is 500. So the formula, it has to do with number of moles now. Mole. So I will say Q is equals to NQF. This is the formula. So Q is going to be 1.5. So 1.5 Faraday is equal to N. You don't know. Charge on aluminum is 3. That's valency. Faraday F. You don't know conversion because F cancel I. So you don't need this. F cancel F. So we have N9 is equal to 1.3 divided by 3. So we give you 1, that is 0.5 mole. That is 0.5 mole of sodium of aluminium. Let's take note of that. So let's see example 5. Calculate the quantity of electricity required to deposit 0.1 mole of aluminium. You take 1 Faraday to equals to 96500 coulomb. Take note of that. To answer this question, Q is equals to NQF. Straightforward. What is N? That's the number of mole, 0.1. What is Q? Aluminium. Remember, aluminium is 3, valency of 3. What is Faraday? Faraday is 1. If you leave it in terms of Faraday, you can leave it as 1 here. 1 Faraday, so the unit will be in farad. So it will be 0, that is, if I leave it as F, if 0.1 times 3, so this one is 0.3 Faraday. But if you have to convert it, it will be Q now is equal to 0.3 times 96500. It will now be in coulomb. So that is the answer. So that is how to apply the formula. Example 6. Example 6. Calculate the volume of oxygen involved at SCP by calculate the volume of oxygen involved at STP by the passage of 0.3 Faraday. Calculate the volume of oxygen involved at STP. You know, it has to do with volume. So you go back to the formula. V is equals to Q times 22. They will give you molar volume of oxygen of gas at STP. Take molar volume of a gas at STP to be 22.4 DNK. So that's the volume occupied by 1 mole of the gas at STP. So Q this divided by QF. You still remember? That's the formula. So calculate the volume. So V now will now be Q is given to be 0.3, so I'll say 0.3 F. That is a Q times 22.4 all over Q for oxygen, remember, is equals to 4. I've explained that. Oxygen is the valence. We have 2 minus here. Then is a diatomic times T will be 4. Don't forget. So this will be 4 times F. F cancel F. You still remember? So we have V is equals to 0.3 times 1.2 divided by 2. So we have V is equals to 3 times 1.12 divided by 2. We have V to be equals to 3 times 0.56. So from here we have V is equals to 81, 15, 16, 16, 1. So 1.68 DNK. That's the volume occupied by oxygen. That's the volume of oxygen involved at the electrode by the passage of 0.3 farad. That is the answer. Example 7. Example 7. Calculate the volume of oxygen involved at STP by the passage of, let me say, 965 coulomb of electricity. Instead of giving it in farad, it's now given in coulomb. How do we do this? The same thing. V is equals to Q times 22.4 DNK. Everything divided by QF. That's the formula. So we say V, I don't know. Our Q now is given to be 965. So times 22.4. You can see this one is not given in farad. So divided by Q is 4 for oxygen times farad. You now convert it. 1 Faraday is 96500 coulomb. Why do I need to convert it? Unlike example 6, where it was given in farad. So why it is in coulomb? 1 Faraday is equal to this 96,500 coulomb. So this cancel this, you have 100 here. So you have V9 is equals to, so 2 here will give you 11.2 all over Q times 100. Later you have 5.6 divided by 100. So it will be 0.056 and DNK. To convert to CNK, multiply by 1000. So if you like to multiply by 1000, it will now be times 1000 to be 56 centimeter cube. So to answer this question, we are given current time. You know your time is given to be 1 hour. This 1 hour is converted to 1 times 9 times 3600. So it will be 3600 seconds converted to seconds. Take note of that. Then current I is going to be 4 ampere. So you have to find the mass. Mass is unknown. Recall the formula. What is Q? Q is equal to, in terms of mass, MQF all over A. Check your notes. You know it's supposed to be N, and N is equal to mass deposited all over atomic mass or mass number. Then we have this. Recall in terms of current and time. So this one has to be converted. So that's why we have this formula. Remember, IT is equals to MQF all over A. So do the substitution. 4 times 3600 equals to, I don't know, charge. It depends on copper. No copper valence is 2 plus. So it's equals to 2. So this is 2. Faraday 1 Faraday is given to be 96500. That is Faraday. 1 Faraday is equivalent to that. All over atomic mass number of copper is 64. So if you make m the subject of the formula, you are going to get 4 times 3600 times 64. Everything divided by 2, 96500. And you are going to get 8 gram. 4.8 gram of copper. That's by using the formula. That is example 8. So this example 9, calculate the current that must be passed into a solution of aluminium salt for 1 hour 30 minutes in order to deposit 1.5 gram of aluminium. So here we have to find the current. We don't know. So no, we are giving mass equal to 1.5 gram. That's all. And we are giving time to be 1 hour 30 minutes, which converted to seconds, which will be 3,600 seconds plus 30 times 60. You convert 30 minutes to multiply to seconds, multiply by 62. So 3,600, 1 hour is equal to 3,600 seconds. So plus 1,800. So this one will be 5,400 seconds. This is our T. Take note of that. So from the formula, Q is equal to, in terms of mass, MQF all over A, and Q is IT, is equal to MQF all over A. That's all. So by making I the subject of the formula, you see that J I is equal to MQF, everything all over AT. So complete it here. I9 is equal to, what is my M? My M is 1.5 times, what is my Q? My Q, to write is copper, is 2 plus. The valence is 2 plus 2 times F, number of Faradays. For 1 Faraday is 96500 coulomb. Everything divided by A, mass number of aluminium. Okay, is it copper or aluminum? It's aluminum, sorry. Aluminum should be 3. It's 3. Aluminum is Q for aluminium is 3. Q is equal to 3. So for aluminium. Atomic mass number of aluminum is 7. So you put 7 here. When you divide 298 ampere. Okay, so 0.22 gram of a divalent metal is deposited when a current of 0.45 ampere is passed through a solution of the salt for 25 minutes. Calculate the relative atomic mass of the element. You know, from this analysis, M is given to be 0.2222 gram. That is what we know. Again, we are giving time to equals to 25 minutes. 25 minutes. Is 25. So to seconds, it will be 25 times 60 seconds. Whatever you get, this would be give you 300 times 5, 1,500. So T is equals to 1,500 seconds. So we have to find A, relative atomic mass. Let me call it A, is unknown. You remember the formula? Q is equals to MQF, and Q here is equals to 2. So why they call it a divalent metal. So the valence is 2 there. So Q is equals to MQF, then all over here. You know, this is the formula. Then A now, that's what we have to calculate. MQF all over Q. All over Q. That is what we have. That is what we have. That is what we have. Uh, so this one will be what is mass? 0.222 times what again? 0.222 times, okay, before that you can say MQF all over. Q is not given, that we know Q to be IT. Remember? Yes. So our A now will now be, what is our mass? 0.222 times the valence is 2 times F. Faraday, that is 965,001 Faraday, all over Q. I, what is our high? Our high is 0.45, that is the current, times time, 1,500 seconds. So this is 63.5 grams. But they say relative atomic mass, so it has no unit. So it is 63. So therefore, relative atomic mass of the metal is equal to 63.5 without putting the unit. So that is the answer. So this is the